So we're going to look at something that you've seen, you've used, you may know a little bit about, but yet how much do you know about an IP address? So what's an IP address? What is an IP address? Do you use them every day? So what does it do for us? When I say IP address, what pops into your head? Internet? Internet protocol. So IP does stand for Internet Protocol. And remember, that's one of those layers in there talked about TCP IP. But now we're going to look at these things as an address. Does anybody go out on the World Wide Web? Does anybody go on the internet? No, certainly not. And so we're going to look at what does this address really mean to us? And so how do we start looking at what a host name, what a socket is? We're going to look at some command line, really geeky, nerdy tools. So we're going to get kind of in depth. And so one of the things we need to do here is we need to kind of set a basis for some understanding about what we're talking about. And so we have a couple of things. You're going to see something called an FQDN, which really sounds horrible, but really all it stands for is fully qualified domain name. So that's one thing we're going to look at. We're going to look at something called a port number. And unfortunately, there's 65,536 port names, and you're going to have to memorize all of them. Or not. So there are that many ports. We're going to look at them. And then we're going to look at IPv addresses, IPv4 and IPv6. And we're going to talk about what they do and what they are. But to get there, we're going to have to go backwards a little bit, or forwards for some of you, depending on how we want to look at it. So pardon my use of this guy here. So the people online, and if you want to come back and look at it, I'm going to try to write up here. So I'm going to pardon my handwriting already. So how many people know what a bit and a byte is on a computer? Ooh, see, that's where we get quiet. So we need to look at what goes on behind the scenes in our computer. So we've already said a computer is pretty dumb. How many numbers does a computer know? 2. So it knows 0 and it knows 1. That's it. Everything we do on a computer, so when you send pictures, when you send video, when you talk to your mom every night because you need to call your parents, right? That's sent via what we call digital, or zeros and ones. And so 1 0 or 1 1, that is a bit. So a bit can be a 0 or a 1. And that's the smallest unit of information that we're going to have. So that smallest unit of information is called a bit, B-I-T. And so you're going to see that term a lot in here. So make sure you write it down, scribble it down, commit it to memory, bit. So there's another term then. So when I put 8 of those little bits together, I get 8 of them. 8 bits equals a byte. A byte, B-Y-T-E. And a byte really becomes something useful. So a bit by itself just says on or off. It's that light switch on the wall. I line 8 of them up, and I can start to put some information in there. And I can start to do something with it. Because now I have a little bit of data I can store. Now, that is the general format. We put 8 of them all together that when we're talking about this. So it's 2s. So there's a power of 2. So we're in binary. So if I come through here, and if these were all, hang on a second, let me hit the erase button. So these were all 1s. This is going to have a value, the largest value I can hold, with 1 byte. And that value in decimal becomes 255. if those were all zeros, that value would be 0, right? Does that make sense? So no matter what numbering system, so if I'm in decimal and I have all zeros, it's all zeros, right? And if I had a decimal system to get to the biggest number, I would write all 9s. But we don't have anything other than zeros and ones. And so when we write the biggest value we can in binary, we write it all 1s, I get the value of 255. So how many different positions are there between 0 and 255? Somebody heard, I heard it, I think I heard it. So there's 256 value sets in there, right? So if we counted 1 through 255, there'd be 255. But remember, in our computer, we always start at 0. So there's actually 256 different possibilities. So the other way we can refer to this, any of these numbers, we can write them just like we did if I said 10 to the second power, you're going to say that's what, 100? Does that make sense? 10 times 10 is 100. So 10 to the second power is the same as 10 times 10, right? And if I said 10 to the third, what is 10 to the third? 1,000, 10 times 10 times 10. Oh, okay. So, well, we do the same thing, but now we're doing it in binary, and so everything is in powers of 2. So if I said 2 to the 8, what's 2 to the 8? If I multiply 2 times itself 8 times, what do I get? 256. Well, we can go through that, and in fact, you're going to need to know these numbers as we go through here. These are going to be numbers you're going to get in your head over and over and over again. So 2 times 2 times 2 times 2 times 2 times 2. We can all multiply by 2, right? Pretty common. So 2 times 2 is 4, times, and again, 8, then 16, then 32, then 64, then 128, and then 256. That is really the basis for a lot of our stuff we're going to do, is this idea that everything is contained in these numbers. So we need to figure out a way to get from binary to decimal, so something we can understand. And we use these in those IP addresses. You use them all the time and you don't realize you see them. You're seeing these numbers. When you go buy a computer and it says, hey, it's got a 1 gigabyte hard drive, oh wait, is that term byte in there? Or I go buy a video game system. And if you're really old, you may remember the NES systems, the NES 64-bit system. And so it really refers to this idea of zeros and ones. Everything we do is based on zeros and ones. Well, these have placeholders, just like they do in the decimal system. So in the decimal system, if I write I suppose it helps if I use the writing again, 111. We have the ones place, the tens place, and the hundreds place, right? We learned that in 2nd grade, probably, 1st grade. Some of you may have learned it in kindergarten. But in the binary system, we have something a little different, because we don't have anything other than the powers of 2. So we still have scroll that up. We still have the 0 power, right? Yeah. Or we're going to call that the ones. So in other words, if I look at this, I say, well, I have the ones here, and that means I have 2s there, 4s there, 8s, 16s, 32s, 64, and 128. That's the placeholder they're at. And so I can figure out the value of this number in decimal the same way I did those placeholders. So if I would set up here and I would multiply, so 1 times 128 is 128 plus 1 times 64. What's 1 times 64? We can all multiply by 1, I hope, right? If I add up the values of those, what do I get? So what's 128 plus 64? You can pull out the calculator if it's, and we know we have a calculator on the computer, right? So how do I get to the calculator on the computer? Hit the Windows button and type CAL, and it'll pop up. Or CALC, and it'll pop up. So if I add those up, what do I get a value of? If I add all of those values up, so let me give you a hint on the calculator too. If you put in the number, if you put it up there, you don't have to use the mouse to put the numbers in. You can use the keypad on your computer to do that. But this is how we convert to and from decimal to binary. Is we need to be able to know where those placeholders are so we can convert back and forth. And you say, well, why do I care about converting back and forth? Because when we talk about IP addresses, you need to be able to convert back and forth. Because we show them and we tell you those IP addresses generally in decimal, but we need to understand what they look like in binary to understand how they work. So, what do we add if we add all those values up? What do we get? You can prove it yourself that I'm not full of it. If you total those up, you should get 255. That value in decimal then is 255. If I write any set of binary in there, I can do the same thing. So this one would be 128 plus 64 plus 32 plus 16. 0 times anything is what? 0. So we wouldn't have the 8 in there. We'd have a 4, a 2, and a 1. So this is another way to represent a number. And so you're starting to see some of those, the more we work on them, that are going to become very common. And we need to see some of those because when we start talking about IP addresses, you're going to see these patterns emerge. So that is how, if you can remember to multiply by 2, you can create this chart and you can go from any binary value back to decimal. So you can process it or think about it a little bit easier in that decimal form. Well, that's great. I got that. We can sort of see that. I'm going to clear this. There will be pieces in this class where you will need to do that. You will need to be able to convert from binary to decimal. But what if I need to go the other direction? What if I have a decimal number? So I want to convert 193, and I want to convert that into a binary number. Is there a way to do that easily? So that same chart that you just had, so if I put in 128, 64, 32, 16, he's opening up something else on 8, 4, 2, and 1. Same chart, but I'm going to take that 193. What's the biggest value up there I can take out of it? So I can take a 128 out, so I'm going to write a 1 right there. And I'm going to subtract 128. So I'm going to have to do a little manipulation there. So 5. So I have 65 left over. What's the next biggest one I can take out of it? So if I can take out the 64, I'm going to put a 1 in there. That's going to leave me a value of 1. Isn't it? 65 minus 64 is 1. Can I take out a 32 out of it? Can I take out a 16? Can I take out an 8? No, 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 no. So as I go through there, that's my binary number that represents 193. So that same chart, being able to write from 1 to 128 by 2 gives us a chart we can use either direction to create that value. And I can double check myself. So I can say, well, did I really get the right number up there? So I go 128 plus 64 is 192 plus 1 times 1 is 193. And so any set of values we can do this with, either forwards or backwards. So I can go from decimal to binary, from binary to decimal. Now, the computer chunks these bits together, and we're going to see them over and over again. But the most common thing we use is 8 of these in one chunk. That's how we write them. That's how we use them. And it gives us some really good value. For most languages, it works really well. So how many letters are there in the English alphabet? 26. And if I had a number for capitals and a number for lowercase and uppercase, and then I had all the numbers and some symbols, you can find that they can all fit inside of that 255. And in fact, we call that ASCII, A-S-C-I-I. And it's the way we first began to look at how we translate words and store it inside of the computer. So a space, for example, is ASCII character code 20. So 20 in decimal, and then we'd have to translate it into binary to what the computer really uses. So this is the way the computer looks at everything, zeros and ones. That's all it does. And it sends huge amounts of them to convert things around. But we need to look at something fairly simple. So let me get back out of here now. So now that we've kind of looked at binary a little bit, and yes, it's in the book, and yes, you need to deal with it. It's not the most exciting thing in the world, but the reality is, it's the world around us. Everything you do is digital, it's in binary. It affects how we do things to a significant number. And when we talk about that network IP address, when we talk about that port number, so I rattled off that there's 65,536 ports. Where did that number come from? Did I just make it up? It's a power of 2. All around us, those powers of 2. So we're going to see that over and over again. And over here we say, well, IP addresses are 32 bits, and they're written as 4 decimal numbers. So we know that it's 4 bits. That's the entire way we navigate around the internet. Is 4 bytes comprised of 32 bits. So we know we can go back and forth. So each decimal number in there tells us something, and we need to be able to figure out what that is. Really? I thought I just went to Google. When I go to Google, what happens behind the scenes? I type in google.com in my browser. What happens? Is it magic? It kind of is an interesting kind of magic, but there's something happening that translates google.com into an address, and that IP address. So if I bring up CMD again, and you guys are going to do this all the time, so get used to this. The CMD, we're going to go to the command prompt. We're going to show you another tool today really quickly. And we're going to show you something called ping. So we've looked at IP config. Now we're going to look at one called ping, P-I-N-G. P-I-N-G. So ping sends us either one or a set of packets depending on how you have it set up. And you'll see there's a lot of switches. And so one of the things we can almost always do with these command line tools, if I type the command line tool and I type the slash underneath the question mark, because I'm going to put some kind of modifier to it, and I type the question mark, almost always it will give me some information. And so in this case, it says, these are some of my options. So I can ping until it stops. I can record counts. I can do all different kinds of things. We're going to use it as is for now. We're not going to add any modifiers yet. But this simple tool that's on everybody's computer can actually be used as a security issue. Something called a denial of service attack. You guys ever heard of denial of a service attack? Not yet. No, we're gonna get there. So let's type ping, and let's type www.peru.edu. And when I do that, it tells me a couple of interesting things. Notice that it says it's timing out. Peru's web server is set to not respond to pings. We can do that with our server. So it's going to time out after 4 tries. And it's going to say, nope, I can't get that. But it also tells me something else. So we typed in www.peru.edu, but what is it actually telling me? It says your ping statistics for 192.168.3.15. Huh. That's what an IP address looks like. That group of 4 numbers is an IP address. So ping can be used. We do it for a couple of things. One, we check to see if a host is alive. So, yeah, we don't really know from this because it says it timed out. But we do know something about it. Somewhere, something translated from Peru.edu that actually said, well, you're really pinging something called WordPress.peru.edu. So our website is actually WordPress.peru.edu. And it gave us an IP address. Well, let's try another one. Let's try Google. So I can do the same thing. So I'm going to ping. And if I ping google.com, Google actually says, well, we're big enough, we will respond to ping requests. And it tells us, did that packet make it? It gives us an IP address. It says we have a time. And another little number out there, TTL. What does TTL stand for? Anybody know? So in the book, you're going to see that TTL stands for time to live. So as we send out those packets, because we don't want them to float around the internet forever, we actually give them a specified death date, if you want to call it that. Time to live. How many hops they can make, how many routers they can encounter before they die. If we didn't, they would just kind of circulate around forever. But, well, that is an IP address right there. 74.125.124.99. So I'm not sure about that, though. Maybe I'm not right about this. Maybe I'm wrong. So I'm going to set this over to the side so I can still see it. And I'm going to go over here. And I'm going to open up a browser window. In this case, I'm going to pop open a new tab. And I'm just going to type that number in there. So I'm going to say 74.125.124. Can't type. .99. And lo and behold, I've managed to arrive at Google. Well, the original, when they first started out working on the internet, we really did just have to memorize numbers way back in the old time. Would that be fun and handy to have to memorize numbers like that? The brain doesn't really want to memorize it. So in between, we have something, a mechanism to convert, when I type google.com, to convert it into that numeric number, which is then converted into binary, which is really how everything is addressed in the world. So we need to work on our addressing scheme. So a couple of pieces we need to kind of put in perspective to start with. So we talked about this a little bit last week, and we said everything that connects to an internet, so every network connection has a MAC address, Media Access Control Address. And that media access address is burned into that card, or it's burned into that device. So if I logged into my phone and I piddled around far enough, and you dug down deep enough, you would find out that your phone has several MAC addresses. And these are also in binary. To make life more interesting, though, they don't show up as binary, they don't show up as decimal. They actually show up as hexadecimal, which is base 16. Do we have 16 numbers in the number system that we use? So you will be able to tell these because they're going to have odd addresses that include letters. Really? I've never heard of such a thing. Well, if you look on your own computer and you pop up that command window again, rather than take apart the computer and try to find these, if I do the ipconfig/all, you're going to see up here that you have something called a physical address. It's my virtualization one. Can't hardly see on this monitor. All right, so there you're going to see a physical address there in the screen. Every one of those is going to be different. And notice it's got all kinds of numbers in there. And it's also got, you'll see it in a couple of other places, you're going to see DNS servers that have those. Oh, no. These numbers are all around us. And they're base 16. Base 16 is a superset of binary, so that we can show even more information really, really quickly in binary. So here is our physical address. So in this case, it's BC-B5-4F AC26EF. Nice. So it uses, so hexadecimal uses 0 through 9, just like the decimal system, and A through F. It adds A through F, so it's base 16. I'm not going to make you convert back and forth in base 16, but it would work very similarly. But I want you aware of what those are. And now that I've made you go through a little bit of that trouble, I'm going to show you a shortcut step. Would everybody bring up your calculator again? If you don't have it already up. All right, if you click on the little 3 pull downs, you should have a couple of options. Click on the one that says Programmer. And notice the Programmer option actually has conversions from decimal to binary, from binary to decimal, into what's called octal, which we don't use very often. That's base 8, and base 16, hexadecimal. So let me pop it up really quickly. So if you see this programmer mode, notice if I type in 125, it automatically shows me right there what that would be in different. So in hex, that's 7D. In binary, it's 01111101. Well, that's pretty slick. So why did I make you go through having to do it manually? Because to understand behind the scenes is pretty important. So that MAC address uses 48 bits, or 48 zeros and ones, to represent a number. And that number is unique to every card plugged into the internet, wireless, wired, whatever. In theory, that gives us some security. It also lets us look up, and it's a troubleshooting technique. So the first 24, or the first half of that address, tell me who the maker of that device is. So if I have a Dell computer and I look up that address, is it going to be a Dell wireless card in there? In most cases, you're going to find out that it's going to show the actual maker of that wireless card. So you may have a Realtek. In this case, I know who the maker of this wireless or this interface on this one, because it actually even pulls that information up and says, hey, it's a company called Realtek. They don't always do that, and if all I have is that number on a card, so there are some databases online you can find, so it can be a really great troubleshooting technique. So here's an example of a wireless access card. This one happens to plug into the computer in a physical manner, and everything is going to have a MAC address. So how many of you have cable modems for your internet at home? A couple of you, 3, 4. How many of you rent that cable modem every month? I don't know. It comes with my cable bill. The reality is you're probably renting that cable modem. And with most cable modems, you're paying $10 to $12 a month to rent that box. Okay. Well, that's part of my internet bill. But you can probably buy one for $50. So after 4 months, could you save money? It's legal to do. The cable companies don't really care. Well, they do because they make more money on it, but they will not stop you from doing that. I buy that cable modem and I want to hook it up, so I screw it into the cable. When I call into Time Warner or Spectrum or Charter or Cox or whoever you happen to have, what are they going to ask for on that modem that you're working on? They're going to ask for that MAC address so they can associate this ID with your name and account and other information and turn on that particular device. So those MAC addresses are pretty important. We have all that. We have MAC addresses, and we're kind of setting up the stage for where we're going to go to. So it's easier to remember for us Google.com, Peru.edu, WhiteHouse.gov than it is to remember a set of numbers. And so we need to talk about what these addresses are. And you're going to see this in web design. You'll see it in some other classes. We have to have a process to go from Peru.edu into 192. Whatever it is that is our IP address. So there's a couple of things that we need to talk about in here. So top level domain. These work backwards. So if I say the top level domain of an address, it's actually that .com, that .peru or the .edu, .mil, .gov, .biz, .net, whatever you happen to see. So there's a couple of examples here. That last part is actually what we call a top level domain. And we do have some restrictions. So I can't go out and register a .edu account for myself, right? It has to be a university, high school, college, something that has the ability to do that. I can't register a .gov address for myself. But I can register a .com, right? I can register that as a commercial account. There are some personal ones now that have come out. There are different ones for different businesses, .biz, .com, because we ran out of them, so people wanted very similar ones. So sometimes people will go, well, it's not the right one. Non-commercials.org. Although, quite frankly, there are some non-commercial entities that are a little flaky that fall under there. So, quick question. What's the latest top-level domain that's come out in the last couple of years? What do you think it might be? What would be one that makes a lot of sense in a weird way to have in there and separate it from the icky side of the internet to the non-icky side of the internet? So, wouldn't it be great if pornography had all of their own top-level domain? So what would be a top-level domain for porn? .xxx? Thanks for volunteering. Whoever knew that. Here's what real weirdly happened, though. So they came out with a .XXX. But they didn't really sell much to the pornography interest. Guess who they sold it to? Everybody that had a web address they wanted to protect. So UNL said, well, I'm going to buy UNL.xxx because I don't want it to be associated with that. Google said, I'm buying Google.xxx. So sometimes it's that weird unintended consequences. The other thing you will sometimes see on those is you'll see an extension after that, like .ca. So you might see .com.ca. What does that CA stand for? Or NZ. There can be a country appendage on there. So you can have a Canadian, or you could have New Zealand. We do that sometimes, so it makes it easier for routing purposes. If you're a website vendor, so imagine Amazon. Are there different tax laws in Canada than there are in the United States? So you may want to route people to see a website meant for the United States. You may want to route people to see one built for Canada. And so we can separate it with that. So these are the idea of our top level down. And we're going to start working on the backwards piece of that, on then how we work. So well, you have to go out and register any address. You can get only certain ones. I can't register .edu accounts. I can register .com accounts. So how do we get from a name to a number, or a number to a name, either way? We have to use something called DNS, Domain Name Services. So this really is how we make that connection. And when we first started, a long time ago, we actually said, well, the easiest way, I'll just make a list on my computer, and I will store them in a text file, and it will say peru.edu is equal to 192.168. Well, when there were 20 websites, that worked pretty well. It doesn't work that well now that we have millions upon millions upon millions of websites. And so we've come up with a unique scheme that allows us to get that information. So we have DNS servers all over. We've got one back there in the closet. When you log into your computer here, it actually can access a local DNS server. So when I say hierarchical structure, that means that there is you can think of it as a pyramid if you want to, where these names are held. So my server back there doesn't hold, so maybe this makes a little more sense. So my domain name server down here doesn't hold everything, but it's got a couple of local entries. If it doesn't know the address for google.com, it moves up this hierarchy, and eventually it could end up all the way at something called the DNS root servers. But it's a hierarchy, more and more. So I store a few, I store here locally things like where the website for Peru is. And when we look at DNS, it asks the computer there, it says, where's this address? Ah, yep, there it is. And in fact, I have to do that here because we're kind of in a weird environment where we're inside of a network, but yet our website is external. And so if I didn't have a special entry in there, you couldn't get to any of our Peru website from here. You could get to Blackboard because it's hosted externally, but not any of our internal servers. So this is kind of that idea. These authoritative servers are way up here. So various companies will own and run these. So very large internet service providers. And at the very top, those DNS root servers. If you want the most valuable target, the thing that is targeted by all kinds of hackers every day, it's those DNS servers. There's 13 of them. And they're the authoritative DNS servers for the entire World Wide Web. 13 machines, that's it. If you could get into those machines and change something, you could make drastic changes. So imagine you have a business Would you like every business? So instead of going to Amazon, it routes to your site at Amazon 2 that you created. If I could get a hold of that control, you could do that. So the way this works really is my computer says, all right, I'm gonna ask for this address. So in this case, they're looking for mdc.edu. It goes up to the local server. The local server, well, if it doesn't have it, it's going to return back and say, well, I don't have it, but I'll look for it at one of the root servers. And so you keep going up that scale, that category, that pyramid, until you get further and further up. So the fact that it happens as quickly as it does is pretty amazing. It is really a robust, amazing system, and the fact that it doesn't break more often, it's truly a miracle, quite frankly. Are there holes in it? Yes. Are there problems with it? Yes. But this is how we make that connection between an address and a name. And so there's a couple of things that are gonna happen. So some of the things we can do though. We also have some pieces that can get complicated because we might actually store some of this information locally in case we do here. Sometimes so my machine there directly can't access one of the name servers, so I have to actually go through the college's server, so it can get fairly complicated. If I buy a website, and some of you may want to do that. Some of you may already have a bought website. So I want to buy a website, bradstuff.com, because I'm going to sell some amazing product. I want people to be able to get there. And if they type in bradstuff.com and half the computers they go to aren't able to get it, that's going to be a problem. So DNS and DNS routing are actually a really great field to be in. A couple of years ago, I had a student taking this very class. And I was a little perplexed after I talked to him a little bit, because he worked for a major hospital here in the state. This is all he did, was DNS routing. He did DNS routing for the hospital, keeping things running for them in terms of, and you got to remember, in the state, some of our large hospitals have partner hospitals, and so he did have a fairly complicated job, but in order for him to get the title manager or get a smooth scale up, he had to complete a college degree. So I'm talking to him, and there was actually a position I was involved with in a hospital, a small hospital, wanted an overall IT director. And I said, well, you'd be really good at this. And he said, well, they're never going to pay me enough. And I said, well give me an idea of scale of what you're. And at that point in time, and this is a few years ago, he's making 190 grand doing this without a college degree. Getting a college degree so he could get the title of manager or whatever and get about a $20,000 to $25,000 salary. Yikes. So the funny part was I'm involved with the hospital down in Fall City, and we were doing some setting up with some telecommunications equipment. So here's the guy in my class. I actually have to call him for advice on how to set up some DNS stuff. It is that specialized in some cases and very narrow. But is it a great field to be in? Yeah. Would I like to make 190 grand a year? That's almost as much as an assistant coach at UNL makes. Well, okay, maybe not. But we have a couple of different types of queries. So you have what's called a recursive. In other words, it keeps asking until it gets an answer of either I do know the answer or I can't find it. And then an iterative query. So our server generally does iterative. So it really only provides information. It doesn't say you have to give me an answer. And so what often can happen when we send iterative queries is we end up with multiple responses back, depending on how we send those up the food chain. So the only problem with that is what if those answers don't match? Well, let's not talk about that horribly yet. So I'm going to skip a couple of these pieces until we get a little further in. So we want to look at this from this perspective. So in this case, this is kind of very similar to what we have here at Peru. We have the big wild internet out here. All of the information in the world lies out there, and a lot of it we don't want in. We have a firewall. We generally have an external DNS server. So the college actually has one. The college has an external DNS server. We have another firewall. So back in my lab, I have a firewall to protect us from the big, bad, horrible internet of the college, and it also does some other functions we'll look at. And then internally, I have a DNS system. And this DNS system internally also ties into what we're going to talk about, something called Active Directory. So how your computers function here work on Active Directory. And so if I didn't have that internal DNS, because the true college one doesn't know anything about what we're doing here on the lab, and if they didn't have one and we just ask a DNS server out on the internet, they don't even have a clue what we're doing in here. So we have multiple layers. It's like an onion to steal from Shrek. There's onions in here. And so we have to kind of keep track of what's going on. And that DNS, when we ask a request, we usually get a lot of information back. And what kind of things it stores? So there's a couple of different records that it stores. So the A record and the 4A record. So the A record, here's an address. It says, this is google.com, this is its address. Well, we haven't really talked about something called IPv6 yet. Everything we've done so far is IPv4. That 192.168.1, those set of 4, is an IPv6. IPv6, so it sounds like it's a bigger address scheme. It is. It uses what they call it the 4A, and at some point they're going to call it the 6A, I think, from what I understand. But it's another record. It holds an address, but it holds an address in IPv6 to a name. You can have alternative names or CNAMEs. You might have a pointer in there, record, that when we go backwards. So if I put in an IP address, I need to be able to go back to what that name is. And then really importantly, we use a lot, and quite frankly, it probably gets hit more than a lot of times the other records, is an MX, or mail exchange record. So how does our mail server translate data from one location to another? So every time you guys log into your email account here, you're getting a MX record, and you're saying, hey, that my mail actually goes to here, this is its information, and that's how it puts these things together. So these are all stored inside of DNS. So at a business, we pay a lot of extra money to get what's called a static IP address. So that means we own or have rights to that IP address. At your house, you don't. Every time that modem reboots, you may get a different external IP address. Well, it would be really handy if you wanted to put up your own web server, or if you're playing video games and wanted to create your own video game streamer server. And a lot of software that needs to communicate out really needs to have that IP address and know what you're sending out. But the problem is, most of us don't want to pay extra. So the provider I have for my internet right now, they're willing to sell me a static IP address. But my price goes from $62 a month with tax to $280 a month with tax. And I said, nope. So I use something called dynamic DNS. And so that's actually a little piece of software on my router that goes out, and every time that IP address changes, sends out that information to all these DNS services on a dynamic level and says this is what it's updated to. So it's very convenient and makes my life a little easier. It'd be better if I had a completely static address, but I'm not willing to pay that. And so a lot of home routers, you're going to find that's a feature. And if you play video games, that may be something that you use quite a bit, especially if you have any kind of a stream server or anything else going on in there. So we have IP addresses, and for the most part, we're going to concentrate on IPv4 in here. So IPv4. So IPv6 is a little bit different animal. In the next edition of the book, the next edition of the Network Plus test is going to have a lot more emphasis on IPv6. And we can kind of look at the math and figure out why that is. And so one of the reasons we're going to have to deal with this is, let me hit there. So chunk gray's fine. So we said we had 4 octets. So the biggest address you could have, if you had a website, is 255, 255, 255, 255, right? Pardon my handwriting. But that's the biggest web address you can find. Now, if you watch the movies, so if you go back and watch, for example, Swordfish, where they're a hacker movie, they're typing in all kinds of IP addresses and things, you'll notice they're typing in like 392 different numbers. They're not real. The biggest number you can have in that IP address is 255. Well, we know that those are worth 256 apiece. So what happens? How many websites can we have with this system? So we know that there's 0 to 255. Let's take your calculator again. Take 256 to either the 4th power or multiply it 4 times. And what do you get? So I have a calculator. I take 256 times 256 times 256. Oop, I have a bigger number in there I didn't want. So that is the biggest number of web addresses you could have. The biggest number. So roughly 4 billion. You think we're going to hit that number? Whoa, wait a minute. Because remember that we have websites that have multiple pages. Does Peru just have one website? Does Google just have one website? And you're going to find out that that number is not accurate about the number that you can use, because you're going to find that we have some special reserved ones we're going to talk about. So you're going to see IPv6 coming out fairly quickly. It's already in use in several countries. The reality is, in the United States, because we're making things work, we haven't moved to IPv6 as quickly as we should. Your phones, if you look at the IP address you're getting, you're going to find that most of the time you're getting IPv6 style addresses, and we'll show you those. But there's a problem with this. How do we deal with it? So, a couple of other things. So we have an IP address. We also have to have something called a socket or a port. So a port, then, your individual computer has a port. So there's 65,536 of them, numbered 0 to 65,535. So a port really can tell us what kind of application that piece of software is going to. So the most common port you're going to see is port 80. Port 80 is web traffic. But it's not the only port that web traffic goes in. So port 0 to 123 or 1023 are kind of the well-known. They're established. So port 443 for secure sockets. Port 25 for email. So you're going to see those are pretty common. And the way we write those is with a colon. So we'll say our address, colon, port number. When we put those together, we put an IP address and we put a put a port together, we create what's called a socket. It can fit into that computer. Well, where else do we use it? All kinds of things. So I use, if you notice in here in the lab, I'm using an iPad, and it controls the screen of the computer. It actually operates on a port. So it knows that when I send a signal to this computer, it goes over port 7026. And that's how I route it back into the system. Because I'm on the campus's Wi-Fi network here, which is not connected to the Wi-Fi network in the rest of it. So I have to route through and create a routing method to get back to here. And it does it based on that port. So we have what's called a port trigger on our router. When it sees traffic for port 7026, it says, aha, I know that traffic, and it goes to this computer. It doesn't go to every other computer in here. It forwards only to this machine because we have that application set up. So ports are the application level. So here we have a telnet service, which is another way to remotely control a system. Telnet happens on port 23. You'll see a lot of those ports come up. We use them for all different kinds of things. But it's how we make that connection to a machine and a specific location on that machine. So we don't have to have web traffic on port 80, for example. I can set up a web server, and I can kind of hide it by the fact that maybe it's some internal usage, and we hide it on port 82 or something. And unless you knew to put in a web address and the port number, you're not going to ever get to see that. Even some home routers, I've noticed, do this, so you can get to their startup pages. They use some odd sockets. But there's 65,000 of them. We use a huge variety of them, and you're going to see here in a little bit on Wireshark how some of those are going to work. How some of that stuff will get around here. But ports, so we put IP, we put ports together, and ports work really with both types. So IPv4, which is our 32-bit address, the thing we're all used to. IPv6 gets bigger. So it's 128 bits. And you think, well, that's only 4 times as big, right? That only sounds like it's 4 times as big. 32 versus 128. Does anybody agree with that? So if we go back to our calculator, so all of our calculators have all the calculator. I should have it here somewhere. Did I get rid of it? Maybe I did. So we can do power in our calculator. So we can do it in the scientific. So we know that we want to go to, and we want to raise it to some power, and we raise it in this case to 32. So that's our maximum number of web addresses that you could have in IPv4. And so if you think about it, though, all the devices we're starting to see. How many of you have a thermostat at home that's got a Wi-Fi access? Nobody yet? You're starting to see it more and more. How many of you have an Alexis or a Google Home or some of these devices? More and more things are using these addresses. So we think, well, if I go 4 times as big, but the reality is because it's a power, so if I did 2 and I raised it to 128 bits, it's far more. So that is a 3 followed by 38 zeros. It is a huge set of address spaces. In fact, it's enough that every square foot on Earth could have its own IP address in IPv6. It's that big. So the reality is we almost need it to work, and we need it to work fairly quickly. Go back here. So we talked about 32-bit. We looked at what an octet is. Well, 0 to 255. We didn't talk about yet why I lied about that you could have 4 billion, because we reserve some of them. And we divide them into these classes. So this makes sense when we had 50 machines, 100 machines, 1,000 machines on the internet, but it doesn't make a lot of sense now. So the biggest thing we need to grab is class A, B, and C. So remember, there's in groups of an octet. So class A, B, and C. So class A says the beginning of it, we control the beginning. We own this number, and we get to put all of these pieces in there. And if you work the math, that means there's only 126 networks available in class A. So that's very large companies, but there's only 126. Internally, each of those could have 16 million addresses. But how do you pick which 126 companies in the world? So you have essentially in the internet as we know it, you can add those up together. You can add 126 plus 16,000 plus 2 million. And the reality is, that's the number of websites and web addresses you have available externally. Does that seem like nearly enough? What about a country like China? Is China bigger than us? Is China in the next few years going to have a bigger economy than we do? Guess how many Class A addresses China has? 0. Is that going to be a problem in today's internet? Yeah. So this is all the internet space we have. And because the way we set this up in these big chunks, it works really well. And you can look at who has these Class A addresses. So if I go even to Wikipedia and I do a search, so my buddy Wikipedia, and I say list of Class A addresses, and it'll generally show up in Wikipedia the first. So this is who has these what we call /8 blocks. So a couple of them aren't even used. Great. So that's even less addresses we can use. So General Electric, level 3, IBM, AT&T, HP, Apple, Ford. What is this? So that's part of HP. AT&T, Halliburton, PSINet, Prudential Securities, U.S. Post Office. Department of Defense has several. Am I seeing any foreign countries in there yet? Huh. This might be a problem. So now we get down here and we have a couple that are assigned to different places, but the reality is the majority of these Class A addresses, those very large blocks, were done by the United States. We're out of address space right now. I start a company. Can I really get a Class A address? Nope, those are all assigned. What am I going to do? And so the reality is, at some point we are going to have to move and switch. So some of these are reserved, but the reality is there's not enough of these to go around. IPv4 does not have enough address space for everything that we need to do. And it's becoming a problem right now even as we speak. So we don't have enough addresses. Even better, when we set this up, some of this just boggles the mind when you think about it now in terms of we have billions of companies and billions of people all wanting to get out on the internet. There's a couple of them that aren't even used. So 0.0, not used, okay. 255, 255, 255, and every instance is already reserved for something called a broadcast message. And we took an entire chunk of addresses. So 127.0.0.1, and it does one thing. On your own computer, if you ping 127.0.0.1, which we'll do, it's called a loopback, it points back to you. Wait a minute, holy cow. So we could have had another 16 million addresses available, and we have it just point to you. So there wasn't a lot of thought of scalability when some of this system was brought out, and some of this dates back to the late 1970s. If I ping myself, do I really need a Class A address to do that? Does that just seem silly? But you can prove it, and I can go back to my ping, which is somewhere in here. So I can say, well, I'm going to ping 127.0.0.1, and that is pinging my own computer. Well, the only really good thing it does is it tells me that my TCP IP stack on my computer works. Holy schnackles, Batman. So, where we're going to leave you today is we really, really, really need to come up with a better system. And guess what? We've had one since about 1994, and what has happened to it? So, we're going to leave you with this idea. We're going to start talking about static addresses, how DHCP works on Wednesday. We're going to look at VirtualBox, and we're going to look at our buddy IPv6. And we're going to talk about IPv6. So read about IPv6. That would be great. Because that's where we need to be headed. The United States, we'll talk in other classes about how we're not the leader in internet speed, we're not the leader in internet connection, we're not the leader in all these things. Guess what? We're not the leader in IPv6. We should be. We should have IPv6 everywhere, and yet we haven't managed to figure out how to implement it yet. So still to this day, we have very little IPv6 infrastructure. If I go to Africa, because they don't have any IPv4 addresses, guess what? They're almost all IPv6. China, IPv6. Guess what we are? We're sitting here. And so it takes a lot of routing and configuration for us to be able to cross over from IPv4 to IPv6. So why haven't we just moved in and bought the barrel of it? We like to be different. I think you're going to find as we start looking at it, it's because people don't want to make a change. So, all right, make sure you've read. We're going to look at something called Wireshark. So if you want to start on that one and put it on your own computer, that would be great. Also, we're going to put it in here on the labs if it's not already. But we're going to try to understand what Wireshark is and how Wireshark works. All right, questions? Yes, I can help you with it. If you're having an issue with the class code, I can probably help you. Let me stop this so I can start uploading it real quickly.